Welcome to the demonstration of the paper utilizing source code patterns in machine learning based bug inducing commit detection models. The author is me, MD Nadim, Software Research Lab, and Dr. Bonani Roy, Assistant Professor and Director of ISC Lab. We both are from Department of Computer Science, University of Saskatchewan, Canada. Let's get introduced with the motivation of this work. We wanted to detect bug-inducing commits from the software system during its revision time, and it will make easily maintainable, increase the reliability of the software system, and make the software system less costly. We can find a lot of examples where these properties have been impacted because of detected software failures or bugs. Here, an example shows that about 606 recorded software failures impacted about 3.7 billion people, 1.7 trillion US dollars in assets, and 314 companies. If we can detect software bugs early, it can help both the software developer and the software industries. So what actually happens? A software system experiences a lot of changes in its lifetime, and those changes are performed by commit operation in its version control system such as GitHub. And the commit operations which induces bug in a software system or problem or inconsistency in the software systems are called bug inducing commits. And the commit operations is done in the source file by commit patch, and we want to utilize the structure of source code from the commit patch to be used in machine learning based detection models. So what we are meaning the code pattern. Here we can see two different code segments. The both segments are doing the same thing, but they are written in different styles. This is a common scenario when more than one developer is working on the same project. Because as developer changes, as developer differs, the pattern of the code could be different. And this difference will provide different coding. These different coding styles will provide different code pattern, and we will refer token pattern and token sequence as code patterns in this study. Now, how we are going to extract this TS and TP? To extract them, let's consider the same code segment and we apply a tool called SourceML to convert them in XML representation. XML representation will provide a hierarchy of tokens, and as the style of writing the codes, both the segments are different, we will obtain different hierarchy of tokens here. And different hierarchy of tokens will provide different token patterns. And we will count the token patterns and use as the feature values. As the token patterns are different, we will also get different token sequence for both the code segments. And we will use n-gram based bag of word from base token sequence and use them as feature value in machine learning models. I want to show another example of another code segment, which applying this code segment will provide this XML representation, and from this XML representation we will get hierarchy of tokens which are referred as token patterns, and also get sequence of tokens which we get the token sequence, and we apply the feature retrieval method, and after getting the feature values we will apply the machine learning model. So those token pattern and token sequence we'll use to encode the commits of a software system. And from those commits, we will try to detect which commits are bug inducing and which are not. Here, I want to show a sample encoding of token patterns to make it more clear. Here, so for example, when commit ID 1 has this token pattern, commit ID 2 has this. Similarly, commit ID 5 has this token pattern. We obtain a unique token pattern and make them as a label of the feature value, and then count this token pattern. For example, TP3 is 2 times here, so we put 2. TP5 is absent here, so we put 0. In this way, we will able to encode each commit by the means of token patterns. Similarly, we will take the bag of word representation of token sequence and encode the commits by using those token sequence. Now, this encoded token pattern value or token sequence could be applied to train machine learning model, and we will keep some a part of the data. Here we have kept 30% data for testing and 70% data for training. The commit ID will uniquely identify each commit. So those feature values will represent those commits in machine learning model, and the label is the label from which we know this commit is bug inducing or not. Now let's get introduced with commonly used features in existing studies. We found the existing studies uses some statistics from the commits, such as how many lines have been added, how many lines have been deleted, how many lines have been modified as the feature values. Some also total line of code, LOC, they use, and the bigger file is more likely to be buggy is the key rationale to take this feature value. And also there are some studies have used developer information, such as experienced developers is less likely to induce bug. And there are some studies which combines all these types of features. We will refer GS as the feature in our study. We will refer all these features as GS in our study. Now, what's the goal of this study? The goal of this study is to compare the performance of bug-inducing commit detection by using TS and TP and very different combination of TS, TP, and GS, and compare that the use of TS and TP providing better performance or not. And here is the GS-based features, and we also want to see that the better results are statistically significant or not. Here is the subject systems we used. Those 6 subject systems, we have some manually labeled data sets of bug inducing, and commits are L is equal to 1, and the other commits that are not bug inducing are L is equal to 0. And we can see that the number of data instances is not very big, but the machine learning model, such as random forest model, is applicable in this size of data sets. We do not use automatically labeled data sets by SGSF algorithm, as we found some study mentioning that the labeling of bug inducing commits by SGSF algorithm is not always correct. And as we wanted to verify our introduced TS and TP features performance, so we rely on these manually labeled data sets. Here is the overall implementation scenario where We took the manually labeled datasets by this study and then retrieved the source codes from their respective GitHub repositories and then extracted each kind of features from the source code and GitHub and then ranked those features by using recursive feature elimination algorithm and then apply classification by random forest model and then compare and reported the results. Here is the overview of our obtained results. These results are represented by using F1 score. We calculated both precision and recalls, and from precision and recalls, we get the F1 score. And to provide the overall view of our obtained result, we are given this diagram here. In our paper, the precision, recalls, and other diagrams are also available to view. Here we can see the feature values we have used and the distribution of F1 score in the y-axis. Here GS all contains all the features from the GitHub statistics. That means we do not prioritize the features. Here GS contains only the important features and all the other features. TS and TP also contain only the important features which we obtained by applying recursive feature elimination process. From this diagram, we can see that if we apply, if we take only the important features, here the F1 score improves compared to the all the features. And when we take GitHub, when we take token sequence features, F1 score improves considerably than both of them. And in all the other cases, so the F1 score is below than TTS, but in all the other cases, the F1 score provides higher value. We get higher F1 scores compared to these two feature values. From this scenario, we can say that the use of token sequence and token patterns provides better results, better F1 scores in all the cases. If we do not use if we only use GitHub sequencer, we non-prioritize GitHub sequence features. We also perform the significance test of our result improvement, and we are going to show the result of significant test in all the criteria. Just when we use where in the precision, recall, or F1 score. If we consider the precision, we find that all the prioritized feature values perform significantly better result compared to the non-prioritized feature values. If we consider recall, we can see that GS and prioritized or non-prioritized is performed not performed significantly better than TP and GS plus TP. That means token patterns and combination of GS and token patterns perform significantly better performance compared to this both. If we consider F1 score, then we get two scenarios. In the first scenario is same as the precision, and where all the prioritized feature values performing better compared to the non-prioritized feature value. And in the other scenario, we can see that combination of token pattern and GS is performing significantly better than GS alone. Here, I'm going to conclude this demonstration where we focus on dealing on these issues where we have shown the encoding of source code patterns which can be used in machine learning model, We compared GS DSTP features to detect bug inducing commits. We found that TS and TP based features improve performance of bug inducing commit detection, and this improvement is also statistically significant. Our future work includes to use the different here as we only used count of token sequence and token pattern. In future, we want to use other calculations such as TF-IDF, count frequency, burst document frequency, and also want to use other programming language as in this study, all the subject systems are Java-based. And in future, we also want to include larger software systems and larger data sets. This is all. Thank you very much for your patience.